starting a new chapter. So we spent a fair amount of time doing equivalent, I guess is the word I'm looking for, differentiation with multivariate functions. Didn't we find out how you differentiate them? It's called partial derivatives. We did chain rule versions of them. And then we spent quite a bit of time essentially solving the equivalent of Calc 1 optimization questions. You know, in Calc 1, where you've given a function and you're trying to find out is it local max and min or an absolute max and min? Well, wasn't that what we did when Lagrange and the max and min? So guess what? We are now going to do chapter 15, and chapter 15 is about integration in multivariate functions. And that is similar, yeah, to Calc 2. Of course, because there's more than one variable, you can imagine it's going to be different as well, right? There's going to be something different about it. Notation. We are going to be working on what are called rectangular regions. So let me try and do a very bad, but the best I can, version of what we're in fact finding. Right. So I want you to imagine that we have a rectangular region. So x goes from 0 to 2 and y goes from 0 to 3. Right. So you can imagine this little rectangle on the floor. Now there's going to be a function z equals f of xy. And that is going to be some kind of, you know, wavy, surfacey thing like that. Can you imagine that this point would hit the surface maybe here, and this one hits it, say, here, and this one hits it here, and this one might hit it up here. And if I join these guys together, we get a thing that looks like this. If you integrate, it's called a double integral. So a double integral of this function with respect to, I can do it any way we want, dx, dy. That is how you would integrate. And since this is first, you do x equals 0 to x equals 2, and the y guy goes from y equals 0 to y equals 3. This is a number. This is a double integral, and it is a number. In Calc 2, wouldn't the integral be called the area under the curve, right? It would be a physical two-dimensional area. This shape that I've tried to draw very badly here is a solid in 3D. So when you do this double integral, you're getting the volume of that solid. Does that kind of sort of make sense in what you get when you find a double integral, right? When you find a single integral in Calc 2, you're finding the area under a curve. When you find a double integral in this case, three-dimensional space, what you're finding is the volume above the XY plane. Because you see the floor starts on the XY plane and it's a volume above. Now, weird things happen. If this surface is below the XY axis, this will be a negative number. So although I'm calling a volume, and it is in one respect a volume, negative numbers can and do happen. But don't you have areas under curves that could be 0 and could be negative, right? So it's okay when you do a double integral if negative 10 comes out. Don't freak out, right? This is just to try and give you an idea of what you're calculating, right? Positive, 0, and negative, right? Now, if you want to know the net volume, don't you just turn the negative number into a positive, right? So if this is negative 20, the answer is 20, and you can have whatever cubic units you've got. You will not see in many textbooks, if any, this notation. They do this. So I'm warning you up front that the notation that I use is a little bit different, but only a little bit different from the notation that you typically see. Now you might say, well, why do you bother about these extra things? It's very, very easy when these regions get more and more complicated for you to lose track of the start and finish values of each variable. So that's just me emphasizing that this is X from 0 to 2, and this is Y 0 to 3. Now, if you look at this, you can tell it's X from 0 to 2, and you can tell it's Y from 0 to 3. But that's because this is a nice rectangle. Can you imagine that in the future that might be a triangle, or a circle, or an ellipse, or some weird whatever it is, right? It's much more helpful to have a start and a finish. So if you don't like this notation, just write that down in the notes, and you're totally correct. But for me, I find it helpful. So let's try a function and do a double integral of it. So suppose I have the function x squared plus y squared, and I want to know the double integral from x from 0 to 1 and from y from 1 to 2, right? Then the double integral would be from x equals 0 to x equals 1, from y equals 1 to y equals 2. The function would be x squared plus y squared, integrate with respect to x, integrate with respect to y. Have you noticed that we're back to dx and dy, not the little curly delta? So these are not partial derivatives, or partial integrals, I should say. These are integrals, right? We don't need or even think in the terms of partial. Now, if you want to really overemphasize things, stick a big bracket around that guy. And what that means to me is do this first and then do the dy guy second. So it's going to be the integral from y equals 1 to y equals 2 dy. Now, integration rules are a little bit different when you do multivariable. Let's do the easy one first. If you integrate x cubed, would you agree that it's power rule? With respect to x, isn't the integral of x squared 1/3 x cubed? Are you with me? Now, what do you get when you integrate a constant? Because y squared is considered a number, right? Like 5. What do you get when you integrate a constant y squared with respect to x?
You add xy squared plus c.
Right. We don't need the plus c, thankfully, because it's got limits of integration, but in general you would. So you just say that. And then you stick in your vertical x equals 0 to x equals 1. You're all happy about that from Calc 2. Right. Now let's see where this thing goes now. It goes from y equals 1 to y equals 2. If you plug in 1, you get 1/3 1 cubed plus y squared times 1. Take away 1/3 times 0 cubed plus y squared times 0 dy. Are you happy about that? Right. Plugging x equals 1 in, you get this. Plugging x equals 0 in, you get this. Now that tidies up, and you get 1/3 plus y squared. And isn't that just take away nothing, so I don't need to worry about it? dy. Are we good with that line? Okay. Now, the good news is that C wants you to do a double integral, but you've got to the last integral. Aren't you back to Calc 2 world? Aren't you just do what you would always do? Yep. So this is 1/3 y plus 1/3 y cubed, evaluated from y equals 1 to y equals 2. So if you plug in 2, you get 1/3 times 2 plus 1/3 times 2 cubed. Take away 1/3 times 1, add 1/3 times 1 cubed. What does that get me? That gets me 2/3 plus 8/3, take away 1/3 plus 1/3, and the whole thing squeezes into 8/3. So that double integral that we're asked to do here ends up being the number 8/3. And if you want to visualize what that would look like, can you imagine a little rectangle over here from x equals 0 to 1 and y equals 1 to 2? So it would be what, a little rectangle probably over here from 0 to 1, and then y being 1 to 2. So oops, it'll be there. Yeah, kind of distorted, but can you imagine where the little rectangle would be? If you did that rectangle right up and it met this surface, the volume of that shape, right, the volume above that rectangle would be 8/3. Are we good?
You need units.
Okay, if you need units, cubic units. I mean, if the thing was in centimeters, I guess it'd be cubic centimeters. Are we good with that, guy? Right, so what I want you to get from this is the process of how to do double integrals, right? How to do double integrals. So let's do a function, xy, and it's going to be e to the power of xy, take away x squared. And I'm interested in x going from 1 to 2 and y going from 1 to 4. Now, you set up the double integral, y equals 1 to y equals 4, x equals 1 to x equals 2 of the function. And because that's there, you do dx first, and then you do dy. To me, brackets are just helpful. Now, here is an interesting property. As long as these integrals both contain numbers, you can switch the order. So isn't that good that it really doesn't matter if you do the x's and then the y's, or you do the y's and the x's? The answers are the same. Isn't that helpful? Can you imagine there might be some situations where integrating with respect to x might be less work than doing it with y, right? That could happen. Rosie, you have a question.
Can you explain again why you're able to switch it like that? Is it related to Clairaut's theorem?
You are allowed to do it, so that's the good news. And your question is a very good one. Is it related to Clairaut's theorem? I'm thinking in my brain, and this is a long time ago when I was at university and they proved things, whether that's how it was proved. I don't think it was proved because of Clairaut, but I think Clairaut basically says that the order doesn't matter. So it wouldn't surprise me if that would be the proof, although I can't cross my heart and say I know that for sure. But my gut feeling is that that would be a proof if you wanted to go down deep. I think it's one of those situations where it's a variable thing, and if the variables don't really change much, you can do it in any order you like, which I guess is what Clairaut says, isn't it? It don't matter if you do the x and the y or the y and the x. So yeah, probably it is Clairaut. The more I think about it, the more I'm convincing myself it is.
So if it was like, sorry,
right.
What
Question?
do you mean? What do you mean by if the variables don't change much?
Oh, I mean, as long as these are numbers.
Okay, so as long as they're numbers and not expressions, you can switch.
Yeah, because later on we're going to do double integrals where it's from y equals x to y equals 4x plus 1, right? Things like that. Then you cannot switch the order. right? So switching the order only works when these things don't matter, or maybe back. As long as these are numbers, how about that? A better way to phrase it. As long as these are both numbers, you can switch the order. Anyone got a particular preference? Do you want to do the X's and the Y's or the Y's and the X's? Any particular preference?
Let's do the Y's first. So
Okay,
then we
let's
can
do
see
that
the
one.
switching in action.
Right. So I'm going to do the integral from x equals 1 to x equals 2. With respect to y, e to the x plus y is just e to the x plus y. Would you agree? Okay. What would negative x squared get you with respect to y? If you integrate negative x squared with respect to y, what would you get?
That would be negative x squared y, because the negative x squared would be considered a constant.
Agreed. And then you would do from y equals 1 to y equals 4. And then you could do the dx later, right? So it's going to be the integral from x equals 1 to 2. If I plug in 4, I get e to the 4 plus y, take away 4x squared. If I plug in 1, I get e to the 1 plus, why am I saying 1 plus y? I should say 4 plus x. And if I do this one, I get 1 plus x. Technically, I should have said x plus 4 and x plus 1, but too late now. Take away an x squared, dx. So now I have a chance to rewrite that as e to the x plus 4, take away e to the x plus 1, negative 4x squared, take away is an add, so negative 3x squared dx. Are you comfortable about those three terms? Right. Plugged in y equals 4, gets x plus 4. Plug in 4, get 4x squared. Plug in 1, get x e to the x plus 1. Plug in 1, got a negative x squared. This guy and this guy combine to give me that. I should now be able to do the next fella. Well, integrate him, you get that. Integrate him with respect to x, you get that. Integrate this guy with respect to x, you get that. And then you evaluate it at 1 and 3. So what do I get? I get e to the 7, take away e to the 4, take away 3 cubed, subtract e to the 4, take away
So what is the limit for x 1 to 2?
Thank you. And now I've got to be careful with this guy. E to the 1 gets me 5 here. E to the 1 gets me squared, take away 1 cubed. And it looks like I'm going to get an e to the 6, take away an e to the 5, take away an e cubed, plus an e squared, negative 27. Now be careful with this fella here, because negative 1, the negative of 1 cubed is just negative 1, but that's an add 1. So negative 27, negative 26, I believe.
Would it be negative 8 because it's 2 cubed?
Ah, did you all catch that mistake? Yeah. We good on 7 then? Negative 8, add 1. Right. Horrible answer, but it is the answer, right? I'm not going to do it the other way around, which is this way, but it will be the same answer. And you can check that if you wish. So far, so good. Right. So we are basically generating some skill set on integrating, finding double integrals over rectangular regions. So I'm just picking one that I haven't done. How about this one? This is a version question 3. And the double integral is from y equals negative 4 to y equals positive 4. And then from x equals 0 to pi upon 2. And the function is a y plus a y squared cosine x, and the x's get first, and then the y's get second. Now, integrating this with respect to x, you get yx. Integrating this guy with respect to x, what do you get if you integrate y squared cosine x with respect to x? Y squared cosine x, integrate it.
Y
That would be
squared
Y
sine
squared
x.
I hear that. Y squared sine x, to have you almost the exact same moment. Evaluated at x equals 0 and at x equals pi upon 2. Let's see what that becomes. Right, you're going to get y times pi upon 2 plus y squared times the sine of pi upon 2. Take away, oh wait a minute, isn't y times nothing just nothing? And isn't y squared times the sine of nothing just nothing? Can I just do that instead of writing the whole calculation? Right, y squared nothing is nothing. Y squared sine of 0 is still 0. And that leaves me with this guy. So we are now going to do pi upon 2y plus y squared. What's the sine of pi upon 2? Almost wrote sine again. It's a number. What's the sine of pi upon 2?
1.
1. So I really just need to do that then, right? And add 1 to the power and divide by the new power. Gets you this guy. Add 1 to the power and divide by the new power. Gets you this guy. And now you've got that. Can I just dot these because they take forever and the hard bit's over, would you agree? Aren't you just going to get some ugly fraction with pi's in it? Probably some numbers.
Oh, would that become pi to the 4th because of the 1/2 y squared?
This one here, yes. Are we good? I'll put that over there for you. Let's do one with fractions in it. So I'm going to do the integral from y equals -2 to 2, and the integral from x equals 1 to x equals 2. And the function is x over y plus y over x. And I'm going to do a dx and a dy. And I'm going to be really careful here because there is a mistake that is very easy to make. Integrating y over x and x over y with respect to x are not as straightforward as you think. Let's just take it simple. If you integrate x over y with respect to x, you could think of it like that, like a half x. Now, if you think of it like that, won't you add 1 to the power and divide by the new power? And so the answer is x squared over 2y. Are you happy about how that happened? That the integral of this is actually that. Right? Add 1 to the power and divide by the new power. Okay. I did more lines than you need, but so we've got this guy. Now the other fella, you got to be careful. This guy is really that guy. But if you do the power rule on that, you will go crazy because it don't work. So what on earth, and I'm going to rewrite it like this, do you get when you integrate y times 1 over x with respect to x?
Negative y over x squared.
No. That's the differentiation. What do you get if you integrate 1 over x? Calc 2,
Natural
1
log.
over, yeah. Do you see how different those two pieces are? You got to have the right hat on, right? You know, you have your differentiation hat on, you have your integration hat. Isn't the integral of 1 over x a log, right? Now, I should be able to plug in the numbers.
Would that be x squared over 2y?
Thank you. And we have 2 squared over 2y plus y times the log of 2. Take away 1 squared over 2y, add y times the log of 1. Now 2 squared is 4, 4 over 2y, partial cancel, 2 over y. Can't really do anything to that, so I'll leave it alone. 1 squared over 2y is just 1 over 2y. This guy, well, the log of 1 is 0, so you actually get that. So, oops, dy. So I'm looking at y equals -2 to y equals 2. And this guy can actually be combined. And now that I'm thinking about it, shouldn't I probably have left that as 4 over 2y, take away 1 over 2y? Because if I thought of it like that, you get 3 over 2y plus y times the natural log of 2 dy. Are you comfortable about those two fractions eventually becoming that one fraction? Same problem with this one. Be careful when you integrate. If you take y times the log of 2, isn't that basically 5y, 2y? It's just a multiple of y. So the power rule comes in. Add 1 to the power and divide by the nth power. Are you happy about that one, having this as its integral? Now the next one I am going to write over here. And I'm going to rewrite it quite deliberately like that. We've came across this earlier. What do you get if you integrate 3 over 2, 1 over y's?
3 halves ln y.
Do you see that it's not that clear when it's written like that you get 3 halves natural log of y? Are we comfortable with that particular question? I'm going to change the question a little bit because I didn't realize that I'd put a limit in that isn't going to work. So I'm making that guy 1. Right. So I'm going to have 3 halves the log of 2 plus 2 squareds the log of 2 over 2. Take away 3 halves the log of 1, which is much nicer anyway, times 1 squared the log of 2 over 2. And what do we get? We get 3 halves log 2, 2 log 2. That's nothing. And this is a half of log 2. So take away a half of log 2. 3 halves add 2, take away that. The whole thing comes out actually very pretty. 3 log 2s. The reason I changed that -2 to 2 is I was scanning and I picked the wrong numbers on one of my integrals, is you cannot find the natural log of -2. Would you agree it's a non-existent value? But if you can find it for 1, so the limit integration has to be at least 1.
Where'd the negative 1/2 ln2 come from?
This one here?
Yeah.
This one? Okay. 1 squared log 2 over 2. See, this is 0, and this is that guy.
When in the bottom, wouldn't that whole thing just be 0 because you'd be 1 squared ln of 1 over 2?
Well, let's look at the two different pieces. One of them said that guy. And the other said that guy. Now, when you plug y equals 1 into here, you get 3 upon 2 log 1, and then 1 squared log 2 over 2. That guy's 0, and that guy is a half log 2. Do you see where it comes from now? That is
because
that's a
the
fixed
LHS
value.
is the constant.
Yeah, that was a fixed value. That was log 2 all the time, whereas the other had the y in it, therefore changes. Are we getting better at these guys? Are better, more comfortable? Right. Let's move on and find. Interesting.
Was that last one a
Uh-huh.
problem from the homework?
And that one was a version of question 4.
Did WebAssign make the y equals -2 the lower
No,
parameter?
I scanned question 3, and question 3 had a -2 in it, and I just wrote down the wrong number.
Oh, okay, gotcha.
So it's just me and my scanning, because I scan sometimes. I scan above or below where I should scan. Right. I'm looking at the next couple of questions. They have different problems to them. Adaptations, I guess I'd call them. Let me show you question 6 first, because I'm going to show you another little trick. This guy is going to be written a little bit differently, but I want you to get used to the notation. Let me try again. So we have a double integral over a region R, and the equation is 3xy squared over x squared plus 1 dA, and then R is described as all the points x, y, such that 0 less than x less than 1, and -2 less than y less than 2. Okay, so this is still a double integral. It's got a little bit difference going on. First thing is that dA is you're differentiating over an area, and this area is a rectangle. So we can basically just call this guy dx dy. So you okay with that piece? Now, based on these limits of integration, I can do x equals 0 to x equals 1, and y equals -2 to y equals 2. And then I'll put in the function 3xy squared over x squared plus 1 dx dy. Are you comfortable at how I transferred that into this? The details are there. They're just writing them, you know, in different versions of the same piece of information. Now, here is a lovely little trick. Do you know we've done the trick where you can switch the order? Right? There is an even more fascinating trick, which I cannot tell you where it comes from because I don't know, except that if you consider one of the variables a constant and the other is a variable, it kind of makes sense that you're allowed to do this. And you might say, what do you mean it kind of makes sense? You can split a double integral into two integrals separated and multiplied. Does that kind of make sense that that could be done? Now, that's not a very common.
It certainly makes life prettier.
It certainly makes life 10 times easier. Would you agree? It's much easier to integrate when there's only one variable to deal with, right?
Is this true always?
It's only true if the function here is separable. The separable means that you can separate the x's and y's. In this case here, I can separate that out by basically thinking out is that, right? So if you can do that, you are. Let me show you where you couldn't do it. These are not separable. Would you agree you can't, there isn't any natural way to split this up without having X's and Y's in at least one place? Now, if I gave you X sine squared Y, could you separate that one?
Yeah.
Yeah. If I gave you X squared Y plus X, could you separate it?
So what we're really
No.
doing is we're just solving
Now you can do it, right?
we're solving an ordinary differential equation at this point with limits, right?
We're doing integrals, not differential equations, but integrals.
Yeah, but it's the same concept, isn't it?
Well, yeah,
Separate-
when you integrate something, you could say you're solving a particular differential equation, because differential equations are normally solved by integrating things. But it's not the way my mind works. But I guess you could say it that way. I just see it as two integrals can be separated as long as the variables can be separated. Right. So
Basically, if there's a way you can factor out a variable and it's like separated by multiplication or division.
you're good to go. Yeah. Since I've just thought of that, or we've just talked about that, let's go back and look at some of the questions. Would you agree you cannot separate out question 3? So you were stuck with doing it the way we were doing it, right? That doesn't separate. Would you agree that doesn't separate? Don't think there's any others. That doesn't separate. And neither does that one. So in other words, you need to be able to do the double integral the boring way, right, the long way, because there are going to be many situations where it doesn't. But when you get lucky, would you agree that that's going to help you? Now, this guy here is a power rule, evaluated at -2 and at 2 times. Okay, how are you going to do this guy? Yeah, Calc 2's been a while, hasn't it? How do you integrate 3x over x squared plus 1?
It's a it's a trigonomic function.
Oh God, I hope not. I mean,
Right.
I wouldn't do it that way. No. Could you? Yes, but don't do it that way. That would take you forever and a day. There's an easier way. You're right, it would work, but there's a much easier way than that. Oh, come on.
Could you rewrite it as 3x times x squared plus 1 to the -1?
Nope. But a good idea. I mean,
This is where we go 3
Integration by
over 3 over x squared plus 1 and then x over x squared plus 1.
No.
Right? And
no, not that.
Is
Okay.
it 3x arctan?
No, I wish it was. Right, it's a U
It's not
sub.
like a U substitution or
It
something?
is, it's a U sub. Okay, let's get this guy out the way, then we'll focus on him. If you plug in 2, you get 8/3. If you plug in -2, you get take away. Oh God, what will you get if you take away that? You'll get take away -8/3. So you end up with 16/3. Okay, so the first guy is 16/3 times. So at the side, we want to integrate from 0 to 1, 3x over x squared plus 1 dx. We're going to do a U sub. Differentiate with respect to x, you get that. You are going to be doing sometimes, at least, U subs and integration by parts. Hopefully you will never have to do a trig substitution, because those guys take forever in a day. So look for something simpler, because it probably will be. Now, if you do the crossover, and then you isolate the dx. And some of you who got other people to show you how to do U subs, you may be doing that using a UDV method, but you'll still get the same answer. So it's going to be the integral of 3x over u, replace the dx with 1 over 2x du. That becomes 3/2 1 over u. That becomes 3/2 the natural log of u, which we then return to the x's. And now we have it. That this fella is 3 over 2, the natural log of x squared plus 1, evaluated at 0 and at 1. So that'll get us 3 over 2, the natural log of 2. Take away 3 over 2, the natural log of 1. That's 0. So all you get is this guy. So we now have 3 over 2, natural log of 2. 2 and 16 will partially cancel. 3 and 3 will completely cancel. And you will have, I believe, a very nice answer, 8 log 2. Are we good with that question? Right. Let's see if I can find another weird one. They're all in terms of vertices. I don't want to do those yet. Well, I guess I could do this one. This is a version of question 11. Actually, it's the last one for today. So it's going to be the integral from t equals 0 to t equals 1. And then from s equals 0 to s equals 1, at least the numbers were nice, 2 times the square root of s plus t ds dt. What I'm going to do first is to rewrite that square root as a fractional power. Okay, you want to integrate with respect to s, 2 lots of s plus t to the power of half. Isn't that essentially just a power rule? Agreed? Add 1 to the power, divide by the new power. So what do we get? We have 2 lots of add 1 to the power and then divide by the new power. And evaluated at s equals 0 to s equals 1. Are you comfortable with what I just did there? Right. If I said to you integrate the square root of x, wouldn't you call it x to the half and do something quite similar? So far, so good. Now, since we need exact values, and exact values kind of goes a long way, style points, I'm going to rewrite this guy as 4/3 s plus t cubed, evaluated at s equals 0 to s equals 1. So what do I get? I get 4/3, plug in 1, and you get the square root of 1 plus t cubed. Take away 4/3, the square root of plug in 0, so you basically get t cubed dt. So now we're getting much uglier looking things to integrate. Now, this fella is now going to be called 4/3 1 plus t 3/2. Take away 4/3 t to the power of 3/2. And the reason I'm doing that is so that I can integrate these expressions also using the power rule. So what do we get? We get 1 plus t, add 1 to the power, divide by the new power. Take away 4/3. Add 1 to the power, divide by the new power. And evaluate at t equals 0 and t equals 1. Let's tidy it up, 4, 2, 8, 5. So 8/15, the square root of 1 plus t to the power of 5. Take away 8/15, the square root of t to the power of 5. If you plug in 1, you get 8/15, the square root of 2 to the power of 5. Take away 8/15, the square root of 1 to the power of 5. Take away, if you plug in 0, you get 8/15, the square root of 1 to the power of 5. Take away nothing. The square root of 2 to the power of 5 is actually 2 times 2 is 4√2. So you get 8 times 4√2 over 15. That's just 1, so you'll get 8/15. Take away that guy, who is also 8/15. That guy gets me 32√2 over 15. Take away 16 over that guy. If I was trying to make this pretty, I'd probably pull out 16 on the top, and that would leave me with 2√2 take away 1 over 15. Okay, you're going to probably have to brush up on your calc too, right? Power rules, U subs, you know, chain rules, all that good stuff, because that's the type of thing that's going to happen in these questions. You probably won't use every single line of working I've got here, but I like to put in more rather than less, because if you go back, you might be able to say, okay, what did he do to get from here to here? Make sure you get your last name, and bye-bye. And I will see you tomorrow. If you do have a question, it'll have to be a really quick one because I have another class to do straight after this one. So last name, bye-bye.